Okay, so at the end of our last video, we talked about how you could look at an area like this that was in terms of x, and you did not have a top minus bottom. And that made us upset that we didn't have a top minus bottom. But one thing I was thinking is, what if I looked at this picture, and then I turned my head 90 degrees to the right? Do I have a top minus bottom then? Oh, I do. Oh, that's cute. Okay, so that's what we're going to do in this video is we're going to find out how to do this area in terms of y, basically going sideways. Okay, so instead of writing our integrals in terms of x, in this video, we're going to write them in terms of y. Okay, so here's how we do an integral in terms of y to find an area. So when we did in terms of x, like in our last video, it was like integral a to b, and that was like my left bound to my right bound. And I did like a top function minus a bottom function. So this is the top and this is the bottom. Now we're going to do something extremely similar in this video, just flipped. So instead of going from the left to the right, we're going to go from a y equals a to a y equals b. Some function in terms of y minus some other function in terms of y. Okay, now when we think about this, when we think about like, here's my y and here's my x, this y equals a, we're saying we're integrating from here to here. So we're integrating from some like bottom to top. So instead of going left to right, we go bottom to top, which makes sense because in terms of y, the plus is on top, the minus on bottom, just like for x, the right is plus and the more negative is on the left. Okay, and then the f of y minus the g of y. When we did a top minus bottom in terms of x, well, top is the positive side. So doing this way, we're going to do right minus left. So again, the more positive one minus the other. Okay, so that's the general setup for how we're going to do an integral in terms of y. So these equations are going to be x equals equations, not necessarily y equals equations. So they're going to be written as x equals some function of y rather than y equals some function of x. So let me give an example here. So suppose, for example, I tell you here is the curve, right? And we have x equals y squared. So x equals y squared, of course, looks just like x equals y squared. It's just twisted 90 degrees. And then we also have the straight line up and down, x equals 4. Okay, and we're trying to find, oh boy, sorry, we're trying to find this pink region inside here. Okay, find the pink region. And hopefully you look at this and you recognize that like a top minus bottom integral like we did in the last video isn't necessarily suitable because the top and the bottom function are the same. Okay, so again, I want to tilt my head 90 degrees and then do a top minus bottom then. So this is like my right function minus my left function. So the way I'm going to find this area is my right function is, let's see, my right function is x equals y, x equals 4 is the right function. And then the leftmost function in this area, if we like draw, horizontal lines across like we drew vertical lines in the last one, the leftmost function is the y squared. Okay, and as for the bounds, just like before, I'm going to set them equal. So I'm going to say, where does y squared equal 4? Okay, so if I set y squared equal to 4, that's going to happen when y equals plus or minus 2, which tells us those intersections right there are at y equals negative 2 and y equals positive 2. So those are my bounds there and there. Okay, so that's the setup. Again, this is my rightmost function, this is my left function, and I integrated from the bottom bound negative 2 to the top of positive 2. Okay, and this integral, of course, is very easy to do. 4y minus y cubed over 3, going for, oh god, this is going to be bad. So this is going to be 8 minus 8 thirds minus negative 8 minus, negative 2 cubed is still negative, so plus 8 thirds, and then I'm giving up. That's just some random number, that's fine. Okay, so that's how you'll find the area. Let's go ahead and look at another one here where you'd have to do this in terms of y. So in this case, I'm actually going to give you kind of the intersections here. So we'll say here's pi over 2. All right, and I'm going to tell you that it looks like this. We have two trig functions here. We're going to have and this is the curve of x equals sine of y. And now in another color, I'm going to come in hot here and do something like this. Okay. And this is the curve x equals 1 minus cosine of y. And I'm telling you, just in the problem, that the intersections here are at y equals 0. And then the other intersection up here, let's just move that. Yeah, the other intersection is at y equals pi over 2. So those are going to be my bounds. So when I want to find the area, it's this pink area right here. Okay, so let's do that. So my area here is equal to the right function minus the left function. And it's a dy. It's going to be in terms of y because we're going sideways. So everything's in terms of y, from our top bound to our lower bound to our equation. So my lower bound is y equals 0. My top bound is y equals pi over 2. Okay, now, what is my right function? Well, again, we could just see looking at this that the right function is the black curve. It's on the right of this interval. So the black curve is the sine of y curve. So that's sine of y. And then the left curve, the blue one, is 1 minus cosine of y. Okay, so again, that's my right and that's my left. Now, when you type this kind of integral in on your calculator, don't feel that you need to type it in terms of y. It doesn't matter what variable you choose. An integral is an integral, right? So you'll just go to Math 9 and you'll say, okay, again, I'm going to integrate the sine of the function minus parentheses 1 minus the cosine of the function. Okay, close the cosine, close the parentheses, I'm subtracted, and then that x is going from 0 to pi divided by 2. Okay. So we'll go ahead and slam down that little integral there, and we'll get 0.4292. Okay. So that's how we'll go ahead and find these areas. So again, the integral is the same in your calculator. It's just in terms, if you want to find the y button right in terms of y, you can, but it doesn't matter. Doesn't matter. So again, we're doing right minus left, and the bounds are like the bottom and the top. Let's do one more. I wanted to go back and look at the problem that we did at the end of the last video. So at the end of the last video, actually, I need to do something else first. You can switch the equations to be in terms of y by solving for x equals. So if you have an equation for the function, you can solve for it in terms of x. So for example, like let's say we have this. So let's say we have the curve of y equals x squared. And we have the curve y equals 3x. Wow, that is not a very straight line here. But y equals 3x, we know it's a straight line that looks like that. And we're trying to find this area in between them. Now, if you want to do this in terms of x, okay, if you want to do this in terms of x, you will set the two equations equal, right? So we do x squared equals 3x. So you solve that out pretty easily. You factor it out. And you find that the bounds there are x equals 0 and then 3. So if you did this integral, the area would be the integral from 0 to 3 of, let's see, the top function is 3x minus x squared dx. And again, this is going from x equals 0 to x equals 3. That's in terms of x. But if you wanted to do this in terms of y, so if you want to do it in terms of y, when you're integrating a right minus a left function, again, what you're going to do is take the equations and solve for x equals. So we're going to solve each equation for x equals. So if you have the equation y equals 3x, if you want to solve that for x equals, you want to get the x by itself, all you do is divide by 3. So x is equal to y divided by 3. If you have the equation, so that's saying this is like x equals 3y. If you have the equation y equals x squared, you can solve for x by taking the square root of both sides, x equals rad y. So I could solve this same problem by just saying, okay, well, if I wanted to do my right function here, that's going to be on the right side, so that's the root y. And then the other function is the 3y. Okay, and as for my bounds, we see one of them is in the origin at y equals 0. And if I want to find the top bound, if x is equal to 3, 3 squared is 9, so that's the point 3 comma 9. So the y bound there on top would be y equals 9. Now again, both of these will give you the same answer. But this is a powerful tool, this idea of like how do we solve for x equals just by taking the equation and isolating x. This area, this integral, will give you the exact same answer as that integral. Now, This problem is obviously less work to do in terms of x, but we're going to see one in a minute that we could do in terms of y that's much easier. And also, maybe you're allergic to your ex. I don't know what they did to you. It could have been a bad breakup. Then maybe doing these problems more in terms of y might be good. So let's go back now to the last problem that we did in the last video, which again asks you to find the area between y equals the natural log of x, and then the area between that and y equals 9 minus x. So when we found these curves in the last one, so we did y equals, we graphed them. When we found the intersection point, so we went to second calc intersect, still no, and we did first curve, second curve there. That intersection point gave us the x and the y value. So it was 7.0473, comma, 1.9526. Okay, now that y bound is going to be useful. Because when we looked at this in the last video, we talked about how there's no top minus bottom. But do you guys agree that in this video, we actually do have a right minus a left function? Like if I'm trying to find this area in here, I have a right function and a left function as I go across, right? I have a right function and I have a left function. And you can see that if you turn your head 90 degrees, right? Oh, there is a function on top. So that's telling you that you can do a right minus left. So we talked in the last video about how to do this by splitting it up into two integrals, but you can also do this with one integral in terms of y. And there's certainly some problems where you need to do it in terms of x or in terms of y. Like, this is an example of something that is just absolutely devilish to do in terms of x, but worked out really easy in terms of y. But on this one, you could do it either way. So in this one, when we do this integral in terms of y, we want to be careful when you solve these. So when we solve these for x equals, when you have the equation y equals natural log x, well, how do we get x by itself? What's the opposite of natural log? Oh, it's e. Right, so we raise e to the power of both sides, so x equals e to the y. As for the other one, when we have y equals 9 minus x, if I want to solve for the x, I'll add and subtract, x equals 9 minus y. So those are my two equations, and a lot of times I'll just write those under it, just so I remember to use them and which curve they go to. Okay, so when I'm setting this up, I can do this area in terms of y as like an integral of right minus a left. So I can just integrate, okay, the right function is 9 minus y, the left function is e to the y. dy. And as for my bounds, we see that the bottom of my area right here is just the horizontal line at y equals 0. So that's my bottom bound. And the top is just what is the y value of that intersection, which is right here. And that's why it's useful to write down the x and the y of these intersections if you're doing it in terms of y. So I'm just going from 0 up to that 1.9526. Okay, and this will give me the same area as the last problem at the end of the last video. Okay, so that's how you convert equations from y equals in terms of x equals by just kind of trying to solve for this x in each one of those. And then that's how we do integrals in terms of y with right minus left. Thanks for watching, guys. Hope this helped. Bring me questions in class. I'll see you soon.